General Specification for Valves, Part 1. General Requirements. All valves supplied for use in oil and gas facilities must conform to internationally recognized standards, codes, and material specifications to ensure performance consistency, reliability, and operational safety. Valves shall be designed, manufactured, inspected, and tested in strict accordance with detailed data sheets, industry codes, and project specifications without deviation unless formally approved. Uniformity in design approach and compliance with the most current engineering practices is mandatory to ensure interchangeability and maintainability. Valves shall be dimensionally standardized to ensure compatibility with existing pipeline infrastructure and adjacent components. Face-to-face dimensions must align with the requirements of widely adopted dimensional standards, particularly for ball, gate, globe, and butterfly valves. Ball valves shall be of the long pattern type unless otherwise specified, and flanged ends must be integrally cast or forged with the valve body to eliminate potential weak points associated with welded flanges. All flanged valves must be machined to a specified surface roughness to ensure proper gasket sealing. Gasket contact surfaces shall have a controlled finish between 3.2 to 6.3 microns, unless otherwise required for specialty sealing applications. For copper alloy valves or other non-ferrous types, flanges must be drilled in accordance with prevailing flange dimensional standards to maintain system consistency and avoid misalignment. Manual valve operation must adhere to ergonomic and safety constraints. The maximum force required to operate a valve at full differential pressure shall not exceed 350 N. Where manual operation would demand excessive force, gear operators must be provided regardless of whether they are specified in data sheets. Gear operators shall be of self-locking, fully enclosed, weatherproof design, complete with lubrication fittings and position indicators for secure, safe operation. All manual valves exceeding designated size thresholds must be equipped with gear operators as a standard requirement. These operators must be compact, robust, and suitable for site-specific climate and mechanical conditions. Handwheel attachments must be configured to avoid interference with insulation, support structures, or adjacent piping during installation and operation. The attachment mechanism must be secure, corrosion-resistant, and easily serviceable. Valves with quarter-turn mechanisms, including all ball and butterfly types, must include locking arrangements to prevent unintended actuation. These locking devices must be capable of accommodating industrial-grade padlocks and remain effective in both open and closed positions. If valve interlocks are specified, top works dimensions must be made available by the valve supplier to facilitate compatibility with the designated interlock system. Heavy-duty valve assemblies weighing more than 250 kilograms shall be provided with at least 2 lifting lugs, appropriately rated and located to maintain center of gravity during handling. Valves in large diameters and high-pressure ratings must be fitted with integrated supporting shoes to distribute load evenly and facilitate secure installation without inducing stress on piping or valve body. For valves exposed to low-temperature service, extended bonnets shall be provided to prevent stem freezing and maintain seal integrity. This requirement applies to valves with design temperatures below -50 degrees Celsius and operational temperatures below -30 degrees Celsius. Exceptions may be considered for non-operable valves within a specific thermal range, provided they meet sealing and emission control criteria through validated testing protocols. Valves must incorporate blowout-proof stem designs as a safety standard. The stem retention mechanism must be independent of the packing gland and designed to withstand operational torque and internal pressure without risk of ejection. All pressure-containing parts, including valve bodies and seats, must include corrosion allowances over and above the minimum wall thickness required, and in no case shall the thickness be less than that defined by the governing design standard. General Specification for Valves, Part 2. General Requirements continued. All valves must be manufactured in strict accordance with internationally recognized codes, particularly those published by API and NACE. Design and performance requirements shall follow ASME B16.34 for flanged, threaded, and welded end valves. Face-to-face and end-to-end dimensions must comply with ASME B16.10, while flange designs must align with ASME B16.5 for sizes up to NPS 24. and ASME B16.47 Series A for sizes NPS 26 and above. Valve end preparations must adhere to ASME B16.25 for butt weld ends and ASME B1.20.1 for threaded connections where applicable. For valves exposed to high temperature and high pressure services, additional references include API 600 for gate valves, API 602 for compact gate, globe and check valves, API 608 for metal ball valves, and API 609 for high performance butterfly valves. Check valves shall be manufactured to meet the criteria of API 594. Fire-safe valves must demonstrate compliance with API 607, soft-seated valves, or API 6FA for fire testing of valves with metallic seats and pressure-containing components. Valves shall incorporate gear or lever operators based on their size and pressure class. The minimum valve sizes requiring gear operation under manual control are defined as follows. For ASME Class 150, ball valves of 8-inch and above, Class 300, 6-inch and above, Class 600, 4-inch and above, Class 900, 4-inch and above, Class 1500, 2-inch and above, and Class 2500, 2 and above. For high-pressure valves rated at API 1000, gear operation is required for all sizes and shall follow vendor's standard while meeting minimum performance thresholds. Where applicable, forged valves are permitted as substitutes for cast valves, but not vice versa. Forged bodies must be produced near net shape to avoid excessive post-processing. Stems must be machined from forged or bar stock and feature an anti-blowout configuration. Welded constructions for stems, gates, or discs are not acceptable. All valves in sizes 6-inch and above may be provided with corrosion-resistant alloy, or a weld overlay, or cladding instead of solid CRA bodies, provided they meet the chemical and mechanical equivalency to the base trim material. Valves exposed to sour or wet hydrogen sulfide service must comply with NACE MRO 175, ISO 5156 requirements. All pressure-retaining parts must demonstrate hydrogen-induced cracking resistance. Austenitic and duplex stainless steels must be supplied in solution, annealed, and quenched condition. For CRA weld overlays and cladding, execution shall be as per industry practices and must pass appropriate quality control checks such as dye penetrant testing and hardness verification. Seat and trim materials must be carefully selected based on service fluids and operating temperatures. Electroless nickel plating, ENP, is not permitted on wetted parts such as balls or seats. Instead, preferred materials include tungsten carbide, stellite, or other approved coatings with high wear and corrosion resistance. For ball valves, solid one-piece cast or forged balls are mandatory. Welded or fabricated balls are prohibited due to potential failure under cyclic or thermal stress. Elastomeric sealing components such as O-rings must be suitable for exposure to hydrocarbons, amines, methanol, and H2S. Viton is strictly prohibited in services with amines or H2S content of 0.2% or more. Preferred materials include HNBR, hydrogenated nitrile butadiene rubber, for high-pressure services, and PTFE or its reinforced derivatives for low-temperature or chemical services. Sealing elements must also be resistant to explosive decompression and certified as such. All valves must be equipped with anti-static devices to prevent the accumulation of electrical charge during flow or operation. For trunnion-mounted ball valves, stem and seat sealant injection points must be provided for 6-inch and larger sizes. Each injection point shall include a check valve, button head fitting, and dust cover. All sealing connections must be constructed from stainless steel and be serviceable under operating pressure without valve disassembly. Valves with mass greater than 250 kilograms must include dual lifting lugs to facilitate safe handling and installation. In high-pressure applications, class 1500 and above, and for valve sizes 16 inches and above, welded-on shoes or supports must be provided to reduce stress on pipeline flanges and ensure load stability. Large diameter valves must also feature drain and vent connections conforming to the same material and pressure class as the valve body. These must be supplied complete with suitable valves, fittings, and identification. Touch General Specification for Valves Part 3, Start General Requirements, continued. Bonnet designs for all valves exposed to cryogenic or low-temperature conditions must accommodate thermal insulation and prevent stem seizure. For valves operating at design temperatures below -50°C or operating temperatures under -30°C, extended bonnets are mandatory. These extensions must be dimensioned to prevent frost bridging and maintain packing integrity. However, valves in the 30°C to 50°C range that are not operated during service may be exempt from bonnet extension, provided they pass fugitive emission testing and meet minimum seal integrity criteria. Body wall thickness for all valves shall meet or exceed the pressure boundary requirements specified in ASME B16.34, with an additional corrosion allowance as specified in the project design basis. The corrosion allowance must be added over the minimum calculated pressure wall thickness. Under no circumstances shall the final wall thickness be less than the value required by the governing design code. This ensures a robust envelope for long-term operation under fluctuating pressures and aggressive media. For low-temperature carbon steel LTCS and carbon steel CS valves, forgings must be fine-grained, fully killed, and delivered in the normalized and tempered condition. Castings must similarly be fully killed and supplied heat-treated to meet impact toughness requirements. Impact testing for CS and LTCS valves shall be performed as per ASME B16.33 or relevant ASTM specifications. All test results must be traceable to specific heat and lot numbers and clearly recorded in the valve certification package. In services where corrosion-resistant alloys, CRA, are used, valves may be supplied with full-body solid CRA construction or CRA-clad CS body construction. Acceptable cladding materials include UNS N06625 Inconel 625, UNS N08825 Incolloy 825, or UNS S327 Super Duplex. Weld overlays must be executed in accordance with established welding procedures and verified by mechanical and corrosion testing. CRA weld overlay procedures shall comply with recognized technical specifications for overlay quality, dilution limits, and minimum thickness requirements. Where CRA body valves are commercially unavailable in large bore sizes, typically 8 inches and above, CRA-clad or overlaid carbon steel valves may be accepted, subject to technical approval. All CRA materials and procedures must be fully traceable and validated by the supplier through mechanical tests and corrosion performance data. Matching of base metal and cladding to trim material must also be ensured for wetted surfaces, flange facings, and pressure boundaries to prevent galvanic corrosion and ensure uniform service life. Seal and seat materials shall be selected based on the expected chemical environment. For floating ball valves, the preferred seat material is PTFE or reinforced PTFE. For trunnion-mounted ball valves, HNBR, hydrogenated nitrile butadiene rubber, is the preferred O-ring material. In cases where HNBR is unsuitable due to temperature limitations, lip seals or PTFE derivatives may be used. All non-metallic seals must demonstrate resistance to chemical degradation, explosive decompression, and thermal cycling within the valve's full operating range. Packing systems must be designed to minimize fugitive emissions. Valve stem packings must be graphite-based and compliant with specifications for emissions control. Acceptable packing materials include braided graphite yarn or graphite PTFE blends that provide low emissions and chemical resistance. Packing configurations must allow field adjustment or replacement without valve disassembly. Packing system design shall comply with tightness classifications defined in emission testing protocols such as ISO 15848-1 or other equivalent standards. Non-metallic seat and seal materials must be supported by documented pressure temperature performance curves from the manufacturer. For high pressure classes 600 sharp and above, or gas service, these materials must be explosion decompression (ED) resistant and supported by third-party test certification. All test data must correlate to the actual valve design, pressure class, and seat configuration offered, and must be available during bid evaluation and final inspection. All valves used in carbon dioxide service must be constructed exclusively from steel. The use of cast iron, malleable iron, ductile iron, aluminum bronze, or copper-bearing alloys in wetted parts is strictly prohibited unless specifically approved in writing. This restriction applies to both the valve body and all internal components in contact with CO2, due to the risk of material degradation and stress corrosion cracking in dry or wet CO2 environments. The supplier must declare compliance with this restriction in the valve data sheet submission. General specification for valves, Part 4. All valve assemblies shall be provided with clear and durable flow direction indicators. For valves that are unidirectional or have preferred flow orientation, such as check valves, globe valves, or specific configurations of ball valves, a flow direction arrow shall be cast, stamped, or permanently attached to the body in a clearly visible location. This marking must remain legible after painting, insulation, or prolonged service, ensuring correct installation and safe operation. Every valve offered shall be accompanied by detailed construction drawings. These drawings must clearly illustrate body configuration, stem and seat details, sealing mechanisms, and pressure-containing boundaries. Enlarged cross-sections of critical areas such as the stem gland, seat interface, and packing chamber are mandatory. Drawings must include part numbering and material identification that match the bill of materials and must be clearly correlated with the item code in the material requisition. Incomplete documentation or generic catalog cuts are not acceptable. Valve manufacturers shall provide complete spare parts listings segmented into commissioning spares, initial operating spares 1 year, and operational spares for 2 years following initial handover. All recommended spare parts must be traceable to their associated valve tag number and include manufacturer part numbers, materials, and estimated lifespans. Additionally, suppliers must provide a consolidated valve bill of materials identifying all components and subassemblies subject to wear or field service. All valves, regardless of type or pressure class, must be capable of performing under the full design range of operating temperatures and pressures specified in the datasheet. This includes accounting for the impact of process transients such as pressure surges, thermal cycling, and startup shutdown sequences. Materials must be suitable for exposure to hydrocarbons, water, sour fluids, and processed chemicals like methanol, amines, or glycols, where applicable. For valves installed in insulated pipelines, provisions must be made to maintain operational accessibility. Quarter-turn valves, ball or butterfly, shall be fitted with extended levers or gear hand wheels located outside the insulation envelope. Suppliers must confirm the maximum insulation thickness that can be accommodated without obstructing operation. This information must be declared in technical submissions and validated by dimensional drawings. Post-weld heat treatment, PWHT, requirements shall follow the governing piping code, typically ASME B16.34, and be extended to include valve weld overlays and fabrication welds where applicable. PWHT procedures must be documented and qualified, with all records submitted during the manufacturing documentation review phase. Where heat-treated components are part of the pressure envelope, the relevant heat charts, furnace calibration, and treatment logs shall be traceable to valve serial numbers. Seal materials and trim components must be selected to ensure long-term compatibility with the process environment. Suppliers must declare the chemical compatibility of offered seals against key constituents such as H2S, CO2, water, NaCl, methanol, amines, and BTX, benzene, toluene, xylene. The maximum allowable concentration for each of these components must be specified in seal data sheets supported by test certificates or manufacturer declarations. The use of unverified materials shall be considered non-compliant. Fugitive emissions control is a critical requirement. All valves shall incorporate low-emission packing solutions and, where specified, must be tested to leakage Class A HS per ISO 15848-1 or equivalent. In addition to prototype qualification, suppliers may be required to conduct production testing on randomly selected valves. Packing systems must be adjustable, replaceable, and serviceable without full disassembly. Seal designs must also demonstrate resistance to both thermal expansion and stem cycling. Pressure temperature ratings for all valves shall be validated by third-party certification and supported by a pressure temperature curve for the full material range offered. Where elastomeric or composite seats are used, suppliers must submit the complete performance envelope for these materials. In high-pressure gas services, Class 2500 and above, high-pressure pneumatic seat testing shall be mandatory at 110% of rated pressure as defined in API 598. All testing must be witnessed or verified by an independent inspection body, and full documentation must accompany the valve at delivery.